Math 1314, Tyler Junior College, Section 4.3, Properties of Logarithms, the product rule. In the previous series of videos, we've looked at exponential functions and their graphs, made an observation that the graph of an exponential function is generally one-to-one, meaning the function is invertible. Defined the inverse of a basic exponential function by reversing the ordered pairs, looking at the graph and all that stuff, and defined the inverse of an exponential function as a logarithmic function. At that point, we proceeded to evaluate some logarithms, and we made note of certain properties. I've listed some of those properties here. Previously established properties include, for any permissible base, meaning positive but not 1, log base b of b is equal to 1, log base b of 1 is equal to 0, log base b of b to the n power equals n, b to the log base b of n power is equal to n, as long as the n isn't negative or 0, log base b of 1 over b to the n power equals negative n, and log base b of the nth root of b to the nth power is n over m. Now you can try to commit all of those to memory if you like. I wouldn't. I would just understand what logarithms are asking you and then answer the question they are asking you. Recall that a logarithm is like a question asking what power turns the base into the argument. The power that turns b into itself is 1, b to the first power is b. The power that turns b into 1 is the 0 power, b to the 0 power is 1. This one's kind of easy. The power that turns b into b to the nth power is n, so the base raised to the nth power gives us the argument. This one's a little trickier to justify because you just can't rewrite it in exponential form. It's already in exponential form. But the trick to remembering this fourth one is that to focus on what the answer to the log does. The answer to a log is a power that turns the base into the argument. So the answer of log base b of n is the power that turns b into n. Well, this is a power on a b, so by its own definition it turns it into n. And then the other two are also just consequences of exponent rules. So I wouldn't memorize these. I mean, you can, don't get me wrong. But if you understand the question a logarithm is asking you, and you're familiar with your exponential rules, then they all just kind of follow, with the exception of the fourth one where you have to think a little outside the box. But in this series of videos, we're going to build some more properties. Properties that we're not just going to build, but we're going to use in the near future. One of those properties is called the product rule. Now, instead of me just putting it up here, let's discover it, make a conjecture, and then we'll actually prove that our conjecture is true. At that point forward, we can assume that it's always true. We're going to solve for x. I know we haven't solved any logarithmic equations yet, but this one we'll be able to solve. Log base 2 of 4 plus log base 2 of 8 equals log base 2 of x. Now, how are we going to solve this? Well, there are two general strategies in solving for any variable in an equation. Number one, simplify what you can. And number two, get rid of what you can't simplify. On the left side of this equation, we have two logarithms that are strictly numerical. So if we ask the right questions, we should be able to get their answers. Let's start with log base 2 of 4. Hopefully at this point, this logarithm is easy to look at and say, I know its answer. But just as a reminder, this is asking you, what power would you put on 2 to turn into a 4? Well, that's easy. 2 to the second power gives you 4. But the answer to the first logarithm is just 2. What about the second logarithm? What power turns 2 into 8? 2 to the third power is 8. Hopefully you know that by now. So the answer to log base 2 of 3, the answer to log base 2 of 8 is 3, because 2 to the third power is 8. Equals, nothing to do over here yet. So we still have log base 2 of x. Hey, but look on the right side, we have 2 plus 3. That's just 5. So now we've simplified this equation to the form 5 equals log base 2 of x. At this point, we really don't have anything left to simplify. So now we need to start getting rid of the things that are in our way. Remember, solving an equation is a goal-oriented task. Your goal is to get the variable by itself. You can do that by simplifying things or by eliminating things. Right now, we have nothing left to simplify, so we need to figure out how to eliminate everything off of the x. So how can we get this x by itself, this x that's currently trapped inside of a logarithm? Well, we could rewrite an exponential form. Rewrite in exponential form. That's a skill we practiced in the previous video series. If we rewrote this in exponential form, you're basically writing down why the answer to the log is what it is. Why is the answer to this log 5? What is the answer to a log in general? The answer to a log is a power that turns the base into the argument. The answer to this log is 5. That's the power that turns this base 2 into equals this argument. Whoa. In one move, we've isolated the x. Well, in one more move. We should at least calculate 2 to the 5th power, but that's just 32. So, what does this tell us? I mean, where's this property, this product rule I keep alluding to? Well, look at the original equation, excuse me. Log base 2 of 4 plus log base 2 of 8 equals log base 2 of x. Well, now we know what the x is. So if we were to substitute the 32 back into the original equation, the equation would read like this. Log base 2 of 4 plus log base 2 of 8 equals log base 2 of 32. Which kind of starts raising questions. Could we have gotten to the 32 faster? Do you see it? Do you see it? It's probably fairly transparent because A, the numbers are small and recognizable, and B, I said we're going to look at something called the product rule. The product of 4 and 8 is 32, which kind of raises the question, will that always work? In math, especially for those of you going into upper-level math classes, it's always a good idea when you spot something, a pattern, a shortcut, whatever you want to call it, to question, is this really a thing, or is it just a coincidence in this problem? I'll tell you right now, it's not a coincidence, because if we had changed the numbers to something that we could work out similarly, and when I say that, I mean logarithms that we can answer, we would get evidence that, yeah, it looks like we can multiply the arguments. So this raises the question, is log base, well, let's make this generic, meaning replacing each letter with a variable, but capture the same idea that's being conveyed. As far as the bases go, all three of them are the same, so we shouldn't lose that characteristic. So we'll call all the bases b. So the sum of 2 logs is equal to a third log. But how can we generically capture the idea that we multiply the 2 arguments, or asking, can we multiply the 2 arguments? Well, let's replace the first argument with a generic argument. We'll call it capital M. Why? Why not? Now let's call the second argument capital N. If we're trying to create a property and then verify if it's true, what should we put over here? Well, the whole thing that we're testing is, can we multiply these 2 arguments when we're adding 2 logs with the same bases to create a single log with the same base, but with a new argument? 4 times 8 is this argument, so m times n would be this argument. Now, at this point, this is still a conjecture. One piece of evidence doesn't make something true. It merely suggests that it might be true. So is log base b of m plus log base b of n equal to log base b of m times n? Well, in the next video, we'll see if this is actually true all the time.